Assalamualaikum and good morning. So today we are discussing about tutorial chapter 3, 3.15. Consider a white liquid film of constant thickness H flowing steadily due to gravity down an inclined plane at angle theta as shown in this diagram. The atmosphere exerts constant pressure and negligible shear on the surface, on the free surface. Show that the velocity distribution is given by U equal rho g sine theta over 2 mu y 2h minus y, and that the volume flow rate per unit width is Q equal rho gh cube sine theta over 3 mu. And you may also compare this result with flow between parallel plates as shown in equation 3.44 and equation 3.45. So let's say we have this situation. So we have an inclined plate like this with certain angle here, and we assume that this is the axis of x, and this is the axis and y, and the thickness, the height of this liquid is h. So and then we need to calculate, we need to try to derive the velocity distribution of this situation. So first, because we are discussing about the x-axis here, so we use the Navistal for x-axis, and I hope you could write the Navistal equation like this one, and then we could simplify everything. So for sure, we are discussing this on the steady flow. So the du dt here is equal to 0, and there are no because it is very white, so we have a white liquid here, so there are no velocity of, means the changes of uy, the value of w here and the value of v here can be neglected, and we also says that the du dx here is equal to 0. So the because it is steady, so all the terms on the left hand side here will equal to 0. So and then because it is stated in this question that the pressure is constant, so means that it's refer, if you see, so the situation here is like an open channel flow, so the pressure is always atmospheric pressure, so we assume that there is no pressure difference. So because it's flow in gravitational force, so we remain the value of gravity there, and again here we assume that du dx is equal to 0, and du dz is also neglected, so we remain the value of d square u over dy square here. So then we could write, we simplified this equation, we could have that mu d square u over dy square from here is equal to negative rho g sine theta. So here we have the rho gx here, but as you could see, the incline here, okay, so the gravity is pulling down straight like this. Now we are talking about the x-axis here. So and then we have the theta here, so we could have the component of the gravity will become g and sine theta. Okay, so we bring the terms of rho g to the left hand side, so we have a negative rho g sine theta. So what we do here is we bring the mu to the right hand side, so and then we need to integrate for 2 times. So we integrate for the first time, we get this term, and we have the constant of C1. So we need to get what is the value of C1 by substitute the boundary condition. So and then if we substitute the boundary condition, so for example, we have the tau is equal mu du dy, and we assume that at du dy at y equal to h, the du dy is equal to 0, because as you know, we have a situation like this, so it's inclined, So the shear stress, so at H here, at Y equal to H at the top here, so the shear stress at this top, we assume it's a very, very weak. So we assume the shear stress, the du dy, is equal to, there are no velocity distribution, means the velocity here is remain constant. So the du dy is equal to 0. So we make the boundary condition, which is du dy is equal to 0, means there are no velocity gradient at the top here at y equal to h. Okay, at this situation is y is equal to h. So we use this condition, we substitute to our previous condition here. So what we get is, so we get the value of C1 is equal to rho g sine theta over mu and h. We substitute here. So here is actually from this equation. So we have C1 here. So we substitute the value of C1 that we get from this calculation. So it's become this one. So and then again we simplify it. So we could factorize the value of y and h like this. So and then we still have du dy, means that we need to integrate for another one time. So we integrate it again. So we have integration of du on the left hand side, and we have integration of all of these in our right hand side. So integration of du, so we get the u here, and then the integration of this, so we get this term and also the constant of C2. So again, we need to find what is the value of C2. So how to get the value of C2? So we need to substitute with the boundary condition. So as we know that in this situation, so we take at the lower point here. So the coordinate of y is equal to 0, and because it is a slip condition there, so means the velocity is also 0. So we substitute the value of u0 at y0, so we get the value of C2 is equal to 0. Then we could write our u here is equal to this equation. So and then to calculate the flow rate, so we just stick to the common equation, which is Q is equal to A times V. So and then we know the u here from what we calculated previously. So I mean from this one. So again, here the u here is at the small u. So the small u means the velocity for each molecule at certain height. So what we need to do is actually we need to integrate the whole situation according to the limit, so that we could get the overall the average velocity. So okay, so for example, if we have this one, okay, so let's say we have a small area here. So what we need to calculate the value of Q here, the flow rate for the small area here is Q times u plus times dy, because dy is the height of this one, and the width here, okay, the width of this plate is assumed to be is 1 unit. Okay, so it means it is dy times 1 by right. Okay, okay, that, and then to get the total flow rate, so we integrate all of this. So Q will become the total flow rate now, and we have u dy in integration form. So in integration, so we have the limit. So the limit is 0 to h. So we substitute the value of u here from the equation that we get from the previous calculation here. So and then we substitute, we integrate with a dy, and finally we could have this, the limit is from h to 0, and finally we could get the flow rate is equal rho g sine theta h3 over 3 mu. Next, we are discussing about question tutorial for 3.16. So consider a film of liquid draining a volume flow rate Q down outside of a vertical road of radius A here. As shown in figure P3.16, some distance down the road, a fully developed region is reached where fluid shear balance gravity and the thin film thickness remain constant. Assuming incompressible laminar flow and negligible shear interaction with the atmosphere, find an expression of VZR and a relation between Q and film radius B. So this is the film radius B here. So and then we have a road here. So and then this road will have the constant radius of R. So this is the situation. For example, we have a pipe here. So and then you flow a water here, and at the middle here, so you have a road. And then now the water is flowing on the road surface like this. So and then as I explained previously, so in flow in pipe, for example, we have a developed region and fully developed region. Okay, so and then we assume that after certain length, so the flow is now in a fully developed region. So let's say from this height, from this level, the flow is fully developed region. So means the velocity is almost constant. So it is steady. And then we need to calculate what the expression of VZR. So here is actually they want us to calculate the film, the velocity distribution for this situation. So because normally vertical axis is Z axis, so they will write calculate the VZ in term of R. Why in term of R? Because we assume that the velocity of Z is not changed in term of Z direction. So it will change in term of R direction because the velocity is become bigger and bigger when the R axis increase as shown in this velocity distribution. So I hope you could understand why the question asked to calculate the VZR here. So again, so we start with the Navistal equation, but now we need to choose the x-axis because the application is clearly show that we need to calculate the element of gravity because gravity is now pulling down the water. So this is the Navistal equation. So we could simplify everything. So we have here is actually will equal to 0 because we assume that it is steady state. So we have the pressure is also can be neglected because it is open to the atmospheric pressure. So we assume that the atmospheric pressure is 0 because we are calculating on gauge pressure. So we have a rho gz here, and then again we could simplify all of this. So we have the uz and u theta is equal to 0, and uz over duz over dz is also equal to 0. Now the only terms that we have is so this term only, and also the gz. So we bring the gravity to the left hand side, and then we could rearrange the equation to become like this one. Okay, so and then you know what to do. So but actually it is a trick here because we have normally we could integrate both. We could integrate 2 times because it is clearly show that we have d square u over dr square, but now we have another term of 1 over r here. So it is not easy to do this one, but the trick is we could use the idea of partial differential. So we have this term. Okay, so if we do, we factorize what we have, so we could write as this one. So and then when we have this one, we could rearrange this. Okay, we bring the r here to the right hand side, so we could have this term. So and then now it is we could integrate both sides. So we bring the dr here to the right hand side, so we integrate, so we will get its own term. So the term of r du dr here, so it's become now at this at the left hand side, and then we integrate the right hand side with dr. So we get this term. And please don't forget to add another constant here. So we show it as C1. So and then again, we rearrange the equation here. So we bring the dr to the right hand side. Okay, and then we bring the r to the right hand side also. So we get this term. So and then we integrate both sides again. So we will get the u now on the right hand side, and then we get all of this term in the left hand side, on the right hand side. So it is we have a ln r here, but don't worry, it can be solved. So as you know, we need to use boundary condition to get the value of C1 and C2, means the constants. So how to determine the boundary condition here, you need to refer to your application. So we have an road here, so and then we have a water down here. So and then the velocity distribution will show like this. So and then we assume that if, okay, this is the radius. So if the radius here is equal to a, so means the velocity here is u is equal to 0. So we get the first condition. And then the second condition, I think you know the tricks from previous question. So at here, so we found that the velocity is actually start to constant. So means that if the we assume that the velocity is remain constant, is start to constant here because the shear stress is very, very low. So we assume that the du dy, so is equal to 0 at y is equal to b. So from where we got the value of b here, you need to see the condition that we have here. So it shows that the distance from here to here is stated as b. So from the diagram, so we get the r equal is b, and the value tau mu du dy is equal to 0. So here it is okay for you to write tau mu du dy is equal to 0, because mu here is cannot be 0. So the only possibility to make shear stress is 0 here by having du dy equal to 0. So this is the meaning of this term. So and then we substitute it. So we could get that the C1 is equal this term and C2 is equal this term, and finally we could substitute in the terms of this one. So we have a C1 and C2 here, so we substitute with the value that we get here, and we could get the velocity distribution is equal to this term. Okay, and then again we need to calculate the flow rate. But here, okay, please do not just remember the equation that we learned from the previous question, because you need to really understand the situation. So in this situation, we have a road here. So and then this road is actually the water will flow around this road. So mean to calculate the Q is equal to A times V. So the V here is actually can be calculated by integrate the U that we have here, but the A here is need to be determined. So the A here is actually the cross-sectional area of this ring. So mean if you see from the top, so this is the road and this is the water. So you need to calculate the ring condition here. So how to get this area? So it's very easy. So if you cut at one point here, okay, it can be stretched like a very thin rectangular here. So the area here is equal to 2 pi r times the dr here, because the dr here is actually the thickness of this ring. So that's the basic idea. So actually we start to calculate the flow rate for the small area at the same radius. Okay, So and then what we have here is Vz is the velocity that flow on this red stripe here. So and 2 pi r dr is represent the area of this red stripe. Okay, so and then we need to integrate this, and then because we integrate with the dr here, so the limit must be reflect the value of dr. So according to the question, we found that so this is dr exists. So this is a 0, so this is a and this is b. So the limit must be from b to a. Okay, so we do the integration. So we integrate with the dr, so we could solve it. So we get this term. Okay, we simplify it, so we could get this term. So and then we substitute the value a and b. So here, so and then we could get the value of q here of this term. Okay, so if we know the exact value of a and b, so we could substitute the a and b, then we could get the value of the flow rate for this situation. Okay, next we are calculating, we are trying to solve question 320 at air at 20 degrees Celsius. And 1 ATM is at rest between two fixed parallel plates 2 centimeters apart. At time t equal to 0, the lower plate suddenly begins to move tangentially at 30 centimeters per second. Compute the air velocity in the center between plates after 2 seconds. When will the center velocity reach 14 centimeters per second? So so this is based on the co-ed flow. So because we have a two plate like this, so we have at least these parallel plates. Okay, might be it start from like this one, and then after a certain time, the lower plate begin to move tangentially at 30 centimeters per second. So it's inclined like this, I think. So compute the air velocity in the center between plates after 2 seconds. When will the center velocity reach 14 centimeters per second? So we are just using the co-ed flow startup, okay, as showing in this one. So we have u over u naught equal 1 minus y over h minus 2 pi, and we have all of this. Okay, so it is shown as equation 3.119. So and then we could get the kinematic viscosity, the nu for the air. For air here is 1.5 times 10 by the power of minus 5. And then we could calculate the Reynolds number, which is, it shows that the flow is laminar. So and then because we want to calculate the velocity, the center velocity, so we substitute the value of y here is h over 2 because this is the center point. So we substitute into the equation, we substitute the value of y here, so we could get this term. So and then we get the dimensionless time delta t here. So we substitute the value of t star with v new mu t, the kinematic viscosity t over h square. So and then we calculate the dimensionless time at the center point velocity after 2 seconds. So we, by using that equation, so we substitute the 2 second here, we could get the t star is actually 0.075. So and then we calculate the velocity at the center point UC after 2 seconds. So we just use, because we only have one reading, so we just take the n is equal to 1 here. So and then the exponent is 2.715. So we substitute the into the equation, so we get the center, the velocity at the center is equal 0.05892 meter per second. So and then we need to calculate the time velocity at the center point reach 14 centimeter per second. So we have this one. So first we need to calculate the ratio, because if you see the previous equation here, so actually it starts with the u over u naught. So the u over u naught means if we have the velocity distribution here, the u is actually showing the velocity inside the velocity distribution, while u naught here is the average velocity. So if the velocity starts to steady like this, so the velocity at the average area here will be written as u naught. Okay. So we start to find uh, the ratio between u center and the u naught. So we find that it is 0.4667. So and then we equalize with the equation that we have. So and then this term is simplified from the equation 1, and then we solve this problem. So we get the t star is equal 0.299. Then we substitute into the equation of t star here. So it is equal to kinematic viscosity nu times t over h square, and then we substitute the value of into this one. So we get, so the h here is equal to so y is equal to h over 2. So and then we could get the time here, it is at around 7.97 or almost 8 seconds. Okay, so the value of h here is actually the gap. So from the question, it is around, if you see the question, it is 2 centimeters apart. And then if you read a textbook, we could have the idea of the development of plane coid flow due to a suddenly accelerated lower wall. So yeah, you could see figure 3.20. So we found that if the u over u here is 0.4667, so we could we arrange is something at this area. So and then we calculated the center. So the center is y over h, so which is y, the center point is 1 centimeter, because the total gap is 2 centimeters, so the ratio is around 0.5. So we have the 0.5 here. So if we draw a straight line here, so it is we find that it is intersect at at almost 0.99 here. So we have a 0.2. If you see, so this line is 0.2. Okay, this line is 0.2 and this line is 0.3. So it is intersect at 0.3, almost at 0.299, because according to our calculation, so the t star is equal 0.299.